Solubility by radicals. And maybe I should give a precise definition. So, definition. The field extension. Maybe you already know it. N over K is called a radical extension. If we have a chain of fields, so where each step we add just some amplitude of some element from the previous field. So if there's a chain, L is the last one, containing Lm minus 1, and so on until say N0, which is our original field of intermediate fields. Such that for all I here, from 0 to m, whatever, we have that Li plus 1 can be written as Li, we adjoin an element Bi, where Bi is a root of a polynomial. So x to the mi minus ai, where ai is an element in L. So as you can see, at each step we adjoin in a simple sense an mith root of an element from the previous field. And then we say a polynomial is solved by radicals if there is a radical extension over which it splits. So definition. A polynomial f in Px is solvable by radicals if there is a radical extension say L over K such that F splits over K. Okay, we are not saying that the splitting field of L over K should be a radical extension. No, because we just want to know whether we can solve it by taking roots. This thing, this L will be usually bigger than the splitting field because we have restricted the way how we can achieve. No, we have, of course, we achieve it in a special way. It's not the minimal way how one can find all the roots. Anyway, okay. Now we want to study this in terms of the Galois group. I think I can give myself a few more centimeters. So solvability by radicals is related to the structure of the Galois group. So the Galois group of F, where the Galois group of F, as you know, is the Galois group of the splitting field of F over K. No? This is not the same as F. So let's see. In order to make sense of this, we need a bit more group theory. Namely, I have to introduce what it means for a group to be solvable. So, introduce some more. So, I want to talk about solvable groups. The definition is quite simple. It also looks slightly similar. So, a group G is called solvable if we can find a chain of subgroups of actually normals. So of subgroups such that each is normal in the previous and the quotient, the successive quotients are abelian. So there's a chain so G is the largest, therefore G0 contains G1 and so on, and the last one is just 1, such that G, so of subgroups, yeah? So each of these Gi must be a subgroup of G and a normal subgroup of the previous one, so such that Gi plus 1 is a normal subgroup of Gi for all I, and the quotient Gi divided by Gi plus 1 is abelian. So being solvable is some kind of generalization of being abelian. I mean, it's a weaker notion, but has something to do with being abelian. And so we have this chain. So all of these are subgroups. The Gi don't have to be normal subgroups in G, but they have to be normal subgroups each time in the previous one, and the quotient is abelian. So one can show, so example, and that's, one can show that Sn is solvable for n smaller than or equal to 4, and not solvable for n bigger or equal to 5. Indeed, what we find, I mean, it's clear that if I take S2, this is abelian. S3 has A3, so the permutations, or the even permutations, as a normal subgroup. So this is just, and this is a subgroup of index 2. So we know that a subgroup of index 2 is always normal, and the quotient is Z2. In fact, it is clear we have seen that Sn has An as a normal subgroup. Of index 2. So, and it's obviously the only index 2 normal subgroup. But if so, the claim is, so one can show that A4 is solvable. And in fact, I think I sketched that to you, if you remember correctly. And so it follows that S4 is solvable. But AN is simple for n bigger equal to 5, so there's no chance this group for n bigger equal to 5 this can be solved. But I'm not going to prove that the n is simple, I just state it. I mean, it's some work. I mean, that's some slightly harder work in group theory to prove it, and I'm not going to try. So, and this would be related to the question well, anyway. Now, in order to apply this story to the solvability by radicals, we need some reasonable criterion for a group to be solvable. And this, yes?
If AN is simple, I mean, if AN is not solvable, does it mean that SN is also not solvable?
Yeah, I think so. Let me see. I mean, you could think. Okay. So I didn't think seriously about it. So anyway, so at any rate, we know. I mean, maybe it doesn't directly follow, but so the easiest way how you could find such a chain of subgroups would be that you start with A2, and but I mean the thing is, yeah, I think what is true. I mean, I haven't checked it, but I think that in addition. I hope that's true. I think it will be true that maybe AN is the only non-trivial normal subgroup. I think that's correct. And so, so we only have a chance, but so it wouldn't follow directly, no? But I think, I haven't now checked this, but I think it's correct to say that AN is the only, so the only normal subgroups of Sn are Sn, the identity, and AN. I think that's correct. And then obviously it follows. So now I want to give a criterion for solvability of a group. And this is in terms of the commutator subgroup. Commutator. What is the commutator subgroup? So we have the following definition. So again, G is a group, and assume I have two elements in A, B, and G. Then their commutator is, you multiply first the product of the inverses, and then in the same order the product of the element itself. So the commutator of A, B is it's denoted like this, and it's A to the minus 1, B to the minus 1, A, B. And so the point is here that if A and B commute, then A to the minus 1, B to the minus 1 is the same as B to the minus 1, A to the minus 1, and then everything cancels out, the commutator is 1. And in fact, it's easy to see that the commutator will be 1 if and only if A and B commute. So And now the commutator subgroup is the subgroup of G, which is generated by all the commutators of 2L. G prime of G, it's usually denoted G prime, and sometimes one even says it's the derivative precisely, of G is the subgroup generated by all elements or commutators A with A and B elements in G. So it's a subgroup generated by all commutators. So if the group is commutative, obviously the commutator subgroup consists of the identity element, because every commutator is one. So clearly we have that G is abelian if and only the commutator subgroup of G is just 1. Because, as you can see easily here, A and B will commute if and only if the commutator is 1. So if this is 1, you can bring it to the other side. So AB is equal to 1 is if and only if A to the minus 1, B to the minus 1. AB is equal to 1, and we can now multiply with these on both sides, which is if and only if AB is equal to BA. Okay. And now we want to relate, we have to somehow want to relate this question of solvability to something having to do with these commutators. And actually we'll have to look at, maybe I should write this. But maybe I can first see at least some hint in the following lemma. So first, this commutator subgroup is not just a subgroup, but it's a normal subgroup. And the quotient is a B. Now we will want to have somehow normal subgroups or something that the quotient be. And this G prime is somehow the smallest subgroup with this property. So if H is a subgroup of G, a normal subgroup, such that the quotient G mod H is abelian, then it must contain the commutator. So as a subgroup. So it's the G prime. Now this was written the wrong way. G prime is contained in A. Okay. So it's the smallest subgroup in a suitable sense of G, such that it's a normal subgroup and the quotient is a B. Every other such group with this property must contain it. Okay, let's prove it. So first we have to bit to understand. As we talk about normal subgroup, we have to see what these commutators have to do with conjugation. So let's look. So if we have an element G in G, we can look at the commutator. I mean at the conjugation of the commutator with this element. So if we write it out, this is G to the minus 1, A to the minus 1, B to the minus 1, A, B, G. But obviously we can put, we can somehow just put in here, we can multiply by 1 here by putting here G times G to the minus 1. We put it in between here. And then we see this is the same as G to the minus 1. This is what I wanted. No, that's not what I wanted. Okay. I mean, I could have done that, but I didn't want to do that. So, yeah, I can put, let me do it in more detail. So I can put everywhere between the elements G and its inverse. So this is G to the minus 1, A to the minus 1. G to the minus 1, so it cancels out. B to the minus 1. G to the minus 1. A, G to the minus 1. B, G. If you look at this, this is just, so I've just multiplied by 1 in many places, and this is just G, A, G to the minus 1. G to the minus 1, AG, G to the minus 1, BG. So the commutator, if I conjugate the commutator, it is the same as conjugating the elements. So in particular, the conjugation of a commutator is the commutator. And we also see, if I take the inverse of the commutator, so if I take AB to the minus 1, this is A to the minus 1, B to the minus 1, AB to the minus 1. If you work it out, this is BA. No? If you just do the inverse is taking the inverse and writing in the other order, this is precisely this. And so, and thus we see the elements. So remember that the subgroup generated by some elements is given by all the words, so all the products of elements, where you either take one of these elements or the inverse of one of the elements, arbitrarily. So as the inverse of this element is also 1, we know that the elements of the commutator subgroup are just the product of commutators. So thus, the elements of T5 are just products of commutators. A, B, and G. So therefore, we can take an arbitrary element in G, we can write as just a product like that, A1, E1 times AN, EN in G prime. This is an arbitrary element. So what is it if we take the commutator of this, G, H, G to the minus, yeah, I want to do it this way. I have, for some reason, used this notation, so I stick to it. And it follows that this is obviously, so we can put G and G to the minus 1, but then you can put also all of them in between here. So this is the same as G to the minus 1, A1, E1, G, G to the minus 1, A2, E2, G, and so on until G to the minus 1, AN, EN, G. And as we have seen, we can pull it inside. This is equal to G to the minus 1, A1, G, G to the minus 1, B1, and so on. G to the minus 1, A and G, G to the minus 1, B and G. So if I take an arbitrary element of the commutator subgroup and I conjugate it with an arbitrary element of G, I get, again, an element of the commutator subgroup. So thus it follows that this commutator subgroup is indeed a normal subgroup. So this was the first. Now, the second statement is quite simple. We just have to see that the classes commute. So let's take two elements A, B, and G. Then we have to ask ourselves, if I take A, G prime times B, G prime, we have to see that's the same as if we do the other round. So obviously, by definition, this is AB, G prime. But now, this AB, I can write as BA times AB. No, you just write it. BA, A to the minus 1, B to the minus 1 goes away. AB, no, this is BA, A to the minus 1, B to the minus 1, AB, and these cancel. Which is B, G prime times A, G prime. So, this is committed. And now, the third statement, we have to see that H is the smallest, that G prime is the smallest subgroup. So assume that H is a normal subgroup. G, and we have that AH times PH is equal to BH times AH or AB in G, which means that the quotient is abelian. What? So then basically we can use the same argument again. So we have that so if I take BAH, this is BH times AH. This is equal, by the story, to AB times H, which now we can again write as BA. So I should actually, let me just, so this is equal to this, right? BH times AH, this is equal to AH times BH, and we know that these two are supposed to be equal. So this is BA times by what we just wrote, AB. H. But this, if BAH is equal to BA times this times H, this means that this thing must be an H. And so as the commutator subgroup is generated by the commutators, it must be contained in H. We have that G prime is contained in H. Okay, so this was this lemma. And now, so we can see that if we take group and its commutator, we find a normal subgroup such that the quotient is abelian. And now, how could this help us to find a way how the group is solvable? We could iterate. We can take the commutator of the commutator. This will be a subgroup of the commutator, such that the quotient is abelian. So if we can keep doing this, so that in the end the commutator is just 1, then we have shown that our group is solvable. And this is actually equivalence. And so this is will be our criterion. So first I have to introduce, to tell you how we want to iterate. So we can iterate taking the commutators. So definition. So we put just G0 equal to G, G1 to be the commutator subgroup of G. And if we view this as a derivative, we can take higher derivatives. So we can take the commutator of the commutator. So we have put G2. We define this as the commutator of G1, commutator subgroup of G1, and deductively Gn plus 1 is equal to Gn. So the commutator group doesn't obviously have to be abelian, but it could be. So by what we have seen, that Gn plus 1 is a normal subgroup. Obviously, these groups are all subgroups of G. And Gn plus 1 is a normal subgroup of Gn. Because, it's the commutator subgroup of that, and the quotient is abelian. And in addition, we have this thing that it's the smallest such subgroup of the nth commutator for all, for anything. Okay, so now we come to the criterion. So, it's kind of clear. We can now do this. We can continue taking commutators of commutators until it somehow stops. And now, if we can do this in such a way that in the end we just get 1, then we have found a chain which makes it into a solvable group. If we can't do it, then we will see it's not solvable. So let me do this. So we have the following criterion for solvability. So the following lemma. So group G is solvable if and only if there exists some n such that if I take the nth commutator of it, it is trivial. For instance, if this n is equal to 1, if this n was equal to 0, the group was 1. If n is equal to 1, the group was a billion, and then so on. So you have to show both directions. So there's the easy direction, because I basically have told you how it goes. So we have a chain of subgroups. So we assume Gn is equal to 1. Then it follows we have a chain of subgroups. And G is equal to G0 contains G1, contains G2, and so on, contains Gn, which is just 1, according to what we have said here. And we have that for all I, G I plus G I plus 1 is a normal subgroup of G I for all I, and the quotient is a B. That's precisely the definition of being solvable. So that's more or less the definition. Now, the other direction. For the other direction, we somehow need to use that this other property that we have, that this the commutator subgroup is the smallest normal subgroup, such that the quotient is a B. So assume G is solvable. Then there's a chain. So we have this chain of subgroups. G is equal to H0 contains H1 and so on, such that again the HI of subgroups with HI plus 1 normal in HI for all I, and HI divided by HI plus 1 is a B. Okay, so this is our assumption. Now we have to relate this to our commutator and use this problem. So at each step, so by the lemma, part 3 of it, we have that if I take the commutator, so we have for all I, if we take the commutator of HI, this is contained in HI plus 1. No, this was the assumption. So thus, so we can use this inductively. So thus, we have that H1 contains H0 prime, which is G prime, H2 contains H1 prime, which is G2, no, H1 prime, which contains G prime prime, because if I apply prime to something, it was more before, which is G double prime. And so inductively, for all I, HI contains G I. No, you just make induction over this. So in particular, if I take Hn, which is 1, contains G n. And so the nth commutator is 1. No, because obviously it's not 0. Okay, so if you have a chain of such things, you actually find there is a chain of at most the same length with in terms of commutator subgroups. So you can just see, each time you do this, you get, it's an easy induction to see this. Just do the same argument. Okay. So this was this, and now the reason why we do all this hocus pocus is actually to prove the following kind of lemma, which we need in the proof, which is something which is in some sense much easier to state, namely, if we have a solvable group and a surjective group homomorphism to another group, then the image is also solvable. So we have the following corollary. Let G be a solvable group. And phi from G to H is a surjective group homomorphism. Then it follows that also H is solvable. I mean, that's very reasonable, no? Because if this group H is in some sense simpler than G, so if this was solvable, this should be solvable too. But it's not so easy to see this directly, but it follows directly from this criteria. So clearly, just by definition of homomorphism, if I apply phi to the commutator of two elements, this is just, the commutator of the images. No, that's just definition. And it follows from this, if I take the subgroup, as I assumed that the map is surjective, it means I get, if I take all commutators in G, I get all commutators in H. So it follows, if I take phi of the commutator subgroup of G, this is equal to the commutator subgroup of H. So it's clear by the statement that the commutator subgroup is mapped into the commutator subgroup. But on the other hand, we have assumed the map is surjective. So if these are arbitrary elements, I can get any element here. So therefore, the map is also surjective. Okay? And obviously, we can apply this thing to higher commutators. Now I can apply this to the restriction of phi to the second commutator subgroup. The same argument applies again. So inductively, we have that if I apply phi to the nth commutator subgroup, or whatever, the ith commutator subgroup for any I, this is equal to the ith commutator subgroup of H. And so in particular, if if we have that the nth commutator group is 1, then it follows that the on commutator of H is also equal.
Question. What would be the problem if we try to tackle the problem directly with the definition?
Yeah, well, I haven't really thought about it. So you want to say you just want to try to prove this corollary directly?
Yes. With the definition of solvable group.
Yeah, I don't know how we can achieve that the different parts, you have this chain of subgroups, and which such that the quotients are normal. I don't know. I don't think it's true that you can deduce. Yeah, well, no, yeah, I mean, I haven't seriously thought about it, but I don't think you can deduce that it works. I mean, you would have to see that the image of this chain is a chain which is property, and I don't think it's true. I mean, that you can prove this, but I cannot, obviously it is true because, I mean, well, it's not a priori here that the image of the chain will do it, but I don't see, I cannot see proof now. And at any rate, independent of that, it's also nice to have this understanding. So it's important to know about commutator subgroups and about these things. So now we want to, however, for our application to Galois theory, we actually are only interested. Yeah, I mean we should have checked whether necessary. So you can, as an exercise, you can think about your question whether indeed one could have just said this, but at least it's not obvious to me. But whatever. So now we want to go back to Galois theory. And let's see. And so we have the following. So the theorem of Galois is, so we take K a field of characteristic 0. So then F, the polynomial F in Kx, is solvable by radicals if and only if the Galois group of F is solvable. Okay, that's a very nice statement. It's actually a bit strange because this Galois group of F is the Galois group of F, so of the splitting field of F over K. Whereas if it's solvable by radicals, the field over which we solve by radical would be different from the splitting field. So it's strange that one could still prove such a statement, but anyway, that's the statement. Now, this is somewhat, it's not completely easy, so we have several steps. First we will be concerned with this. We want to prove that if it's solved by radicals, then the Galois group of F is solved. This in particular means that, whatever, if the polynomial has degree 5, then this might not always be the case, we'll see later. So now we need first some preparation. So if F is solvable by radicals, then we know there exists a radical extension say L of K such that F splits over L. And then we would be supposed to somehow study this radical extension and somehow come to this conclusion. But the thing is, if you look at our theorems, like the fundamental theorem of Galois theory, we know reasonably well how to deal with Galois extensions. But if an extension is not a Galois extension, we don't have so many, we cannot say that the intermediate fields are related to subgroups or any such things. So that's a bit of a problem. So therefore, in order to make this proof, we want to see that we can reduce our proof to the case when there exists a radical extension which is also a Galois extension. Okay, so then we have at least some of our theorems at our disposal. And so we first have to do that. This is the first step, some kind of reduction step. This is unfortunately also not completely simple. This is the following theorem. So again, K is a field of calculus with 0. So let L over K be a radical extension. Then there exists a field extension L prime over L such that L prime over K, so if I take the field extension over K, is a radical Galois extension. So it's both a radical extension, so given by this chain of these things, but it's also a Galois extension. So we somehow have to, and so then we have this reduction and we can deal with that. So, and this is a bit, it's somewhat similar to some of the trick is somewhat similar to something we used in the proof of the fundamental theorem of Galois theory. We'll see in a moment. Proof. We will make an induction over the degree of L over K. So, if the degree is 1, then it follows that L is equal to K, and the thing F already splits over K, and obviously K equal to K is a radical extension, and we can take L prime equal to L is equal to K. Okay, so there's nothing. No? So now we have to make the induction step. So we assume, and that is obviously much more difficult than this, so assume that the degree of L over K is bigger or equal to 2, and the claim is true for all radical extensions of smaller degree. And so the claim, if the extension is smaller than this, if you have such an extension, then it's a radical extension and exists a radical Galois extension over it. Is true for all radical extensions F over K, which degree is small. Okay.
Question.
Yeah.
Why all radical extension should be finite field extension?
I think I have well, that follows, no? I mean, so if I make a chain, it's a finite chain. And at each step, you join one element. Yeah.
extension of a simple extension of a simple extension of a simple extension should be a finite extension also.
Yeah, it's always a finite extension. No, a simple algebraic extension is finite. And these are always algebraic extensions because the degree of the extensions is equal to the degree of the minimal polynomial.
Yes.
Okay. So now we have this, and now we want to somehow now we therefore can apply the induction hypothesis to this f. But we want to first see, so, what f do we take here? So as L over k is a radical extension, we have this chain of fields where each time is obtained by taking a root of x to the n minus something. So we can take the last step of it. So we have L contains a smaller field by adding something, and we take this as our f. So as this is a radical extension, there exists an intermediate field. So f, so in between these two, such that f is, strictly contained in L, and f is obtained from f by adjoining one element b, which is the nth power of something. So such that exists n greater than 0 with b to the n is an element in f. Okay? So we know that L can be obtained from K by a chain of such things, so we just take the last one before we reach L. I have some rather tired audience. I hope I can still. Okay. So now we can apply the induction hypothesis. So as the degree of f over k is smaller than the degree of L over k, and induction, we get that there exists a field extension f prime I should have maybe said something more. No, that's okay. So I maybe should have said, just to be clear. So the assumption also is we have this whole chain. This is the previous step in the chain, this f. So it means that f over k is also a radical extension, no? No, the idea is that we have this whole chain which stopped one step before reaching L. So each intermediate step is a radical extension, and so on. So there exists such a field extension, f prime of f, such that f prime over k is a radical Gottshe extension. No? So this is the induction. So as it's a Galois extension, it means that f prime is a splitting field of some polynomial with coefficients in k. So that's F prime is the splitting field. Of what do I want to call it? A polynomial F with coefficients in K. Okay, so we have to remember this polynomial F. And now we do some construction similar to what we did in the proof of the fundamental theorem of Gottshe. So we take G to be the Gottshe group of this F prime over K, and we write down a polynomial which somehow takes into account this whole Gottshe group, but also that you want to take roots. So this nth root, so we write down G, is the following polynomial. This is equal to the product over all phi in G, x to the n minus phi of e to the n. So b to the n was this element in F, and so this was the Gottshe group, this thing. So this a priori is a polynomial in with coefficients in F prime. No, so this is this b to the n is an element of F. An element of the Gottshe group of F prime over F sends F prime of F prime over K sends F prime to itself, and as F is contained there, it sends Bn to some element of F prime, and this is fine. But we have the usual thing. We have summed over the whole Gottshe group. So if we apply some element in the Gottshe group, some other element in this Gottshe group, to the coefficients of this polynomial, then by the same trick we used a few times, this is the same as applying this element in the Gottshe group to this argument. And then we just have reordered it here. So you see G, so G is invariant under this Gottshe group of F prime over K, or which was G. Maybe I shouldn't have called G. So thus G is actually a polynomial with coefficients in K. So we have written down in this complicated way the polynomial with coefficients in K. So now we take the splitting field of this polynomial over F prime. Let me see. It says over F. Let's see. Yeah, I think so. Yeah. So we take the splitting field of this polynomial over F. So let L prime be the splitting field of G over this field F. And we claim that this will be the one that we want. So this is now a radical Galois extension which contains our F.
Okay. So can you repeat again why G is invariant?
Yeah. So I said it. So the thing is, it's always the same. I mean, we only used it once before, so always it's a bit exaggerated. So we have some polynomial product over all phi. So if phi is an element, is some field automorphism. They apply phi to some So first let me write it like this. So assume we have f is equal to sum ai x to the I is some polynomial with coefficients in some field. And I can also write this, and I also have a splitting. So assume, for instance, it starts with x to the n, so it's monic. So assume that this is equal to the product I equals 1 to n x minus, say, bi. Maybe these bi are in some extension, so like on the splitting field or something. So we have this splitting, so assume we have this. So now we apply field automorphism to the coefficients of that. Then if I take sum I equals 0 to n phi of ai x to the I, then if you just multiply it out, this is the same as the product I equals 1 to n x minus phi of the I. So that the coefficients are invariant under, so applying the homomorphism to the coefficients is the same as applying homomorphism to these roots. And so if this product, so if this happens to be equal to the same, so if this were equal, so if this is equal, then it follows that ai is equal to phi of ai for all I. So the polynomial is invariant. And now this is the case here. So we have this polynomial, we've written it in terms of such a splitting. I mean, it's not quite the same, we have the x to the n, but that doesn't change the argument. And we have the product over all phi in this Galois group, so this was the Galois group of f prime over k. Okay, now assume you apply to this an element in the Galois group of f prime over k. So if you apply psi to this, so assume psi is an element in the Galois group, then you would apply psi to this. But now you see, if you multiply over all psi times phi for phi in the Galois group, is the same as if you multiply over all phi, because you just have shifted it. No? So it's the product of, where psi obviously is an element in the Galois group. So if I take the product over all elements in the group, if I before multiply them by a fixed element, it's still the same product. And so therefore it's invariant. Okay, so now let me see where I was. So I take the splitting field of this polynomial here. Obviously now I have to get rid of psi. Of this polynomial over this polynomial f that I had given myself. Now, and I claim that does it. So we want to show that L is contained in L prime. So this is the subfield. L prime over k is Galois, is a radical extension and Galois. Okay. As I told you, Galois was supposed to be relatively radical, so it's I mean, at least for his times. I mean, for nowadays, I wouldn't say he was for some kind of democracy, but anyway, so that's that. So we have to show that this statement. And so let's see. Where did I put my push the paper? Okay. So first, so I claim L prime, so we show BC, L prime is the splitting field of f times g over k. How does that come to pass? So we have that f prime is, so I could also, why would I say this? Maybe I put f prime. So, it's anyway to say. So we have that this is the splitting field of this f. It's a polynomial in kx. And now I take over this f prime, I take the splitting field of another polynomial whose coefficients are also, which also is a polynomial in kx. And I claim it follows almost immediately from the definition that then L prime is the splitting field of their product. So this is, for the moment I write it as an exercise. So if f and g are polynomials in kx, and say, now I should have different numbers maybe, L1 is the splitting field of f over k, and L2 is the splitting field of g over L1. Then it follows that L2 is a splitting field of f times g over k. No, because you can see, obviously, f times g will split over L2. And because g splits and f splits already before. And on the other hand, you need in this field to have all the roots of f and all the roots of g in order to be the splitting field, and then it follows. I mean, anyway, it's you can easily check this from the definitions. Maybe I should give you this as a homework. I might still, but it's really simple. So given this, so therefore we have that L prime is the splitting field. Does it follow that L prime over k is a Galois extension? Because we're in characteristic 0, so we only need normal, and so it's enough, and it's a splitting field. So you have to show, only to show L prime over k is radical. Well, maybe also that L is an L prime, but that actually, yeah. And so first maybe let me show that L is a, so this comes in a moment. Furthermore, we have that B is a 0 of G. If you put B into this thing and phi equal to the identity, x to the n minus b to the n certainly has b as a 0. So one factor has 0, so b is a 0 of it. So it lies, therefore, in L prime. And we also have, by definition, f is contained in f prime. Thus it follows that L, which was equal to f of b, is contained in f prime of b. So, and this thing contains, so L contains f prime, which is contained in L prime, because F prime is contained in L prime and E is in L prime. Okay, so this is a zero of it, so therefore, therefore we have what we wanted, we have the statement we wanted that L is contained in L prime. And now we have to show, we only have to show that this is a radical extension. So we know that L prime over F prime is the splitting field of G over F prime. So thus we know that the splitting field is always generated by the zeros of G. No? So that means if you add all the zeros of G to F prime, you get L prime. No, that was one way how one could describe the splitting field. And every root alpha of G satisfies obviously this equation. G of alpha is equal to the product of all phi in G, alpha to the n minus phi of e to the n is equal to 0. So, so this product can only be 0 if one of the factors is 0. So, so that is alpha to the n is equal to phi of b to the n for some phi in the Galois of f prime over, what was it, over k. And this phi of b to the n was an element. Okay, and phi of b to the n is an element in f prime. So we had seen that. So we had that f prime over k was a radical extension. So we only have to show that the last step, is again given by extracting a root. And here we see that if I take any of these alphas here, but take any roots of this G prime, it's given as a root, as an nth root of this element, which is an element of f prime. So we maybe have to do it several times. We maybe have to make as many steps as these factors here. But each time we just add an nth root of an element of f prime in order to get L prime. Is that clear?
Excuse me, I'm a bit lost. Why f prime is radical?
That was the induction hypothesis.
I haven't well understood why.
This was, in the induction step, we had
we have f is radical.
F is radical, and we induced the induction step, and we used the induction step to see that it is radical and Galois. Because we make induction over the degree of L over K. F over K has a smaller degree, and so therefore, by induction, there is an F prime, which contains F, which is radical and Galois. Yeah?
Yes, I haven't well understood why the phi of Bn is in F prime. Ah, no. Okay.
No, that's
It's in Galois.
that's by definition. So this is an element in the Galois group of F prime over K. So the Bn itself is in F, and so the phi of Bn is in F prime. Anyway, so it's a somewhat. Now I don't have much what do I do now? Yeah. So, let me see if there's anything sensible I can say. Because now this finishes the proof. First, I want to make sure maybe you understand it. And now we would come to the proof of this one direction of the theorem using this fact, where we now make this additional assumption. So I can maybe start. I should, but I will not say much. I mean, in particular, this takes at least half an hour, I think. So the proof of, let me see, I can just make it first. So we will have to basically, now we have to use all the things we know. So we assume that f into x is solvable. So let L be the splitting field of f over k. And then, by definition, the Galois group of f, I mean, strictly speaking, the Galois group of f over k is equal to the Galois group of f over k.
Of L?
What?
Of L? L is the splitting field.
Of, I don't know why I didn't write it, of f.
I mean the definition of the Galois group of f.
Yeah, so this is of f, yeah, sorry, yeah, I don't know why I mixed splits, but anyway. So it's the Galois group of L over k. So we have to show the Galois group of L over k is solvable. As I say, it's a bit tricky. So let's see. We know that f is solvable by radicals. So we have a chain. So thus it follows there exists a chain that writes now the other way around, k equal to k1 containing k2 equal to k of alpha 2 containing k3 equal k2 of alpha 3 and so on. The last one is named kn equal to kn minus 1 of alpha n, such that at each step for all I bigger than 0, yeah, I don't know why, then now this use all this notation, such that for all I bigger than 0, there exists an Ri bigger than 0 with if I take AI, which is alpha to the I, this is an element in Ki minus 1. Okay, now that's that it's solvable, and obviously, so there's something, such that f splits over k. No, that means that it's solvable. At each step, we add some rith root of some element from the previous field, and at the nth step, we are able to split it.
This index is a subscript.
What?
Alpha Ri.
Yeah. This has a subgroup. This is alpha I. Sorry for the misprint. So it's just the ith, no? So this is always, you get the n plus the nth by, so the ith field by adding the ith element to the I minus first. And furthermore, by what we just proved, we can assume that we have a Galois extension. So furthermore, by the previous theorem, we can assume that Kn over K is Galois. So now how would one want to proceed? So now we know that if we just take somehow the splitting field of something to like x to the n minus ai, or x to the ai minus ai, so if we take the, so we know, if we take x to the ri minus ai, if we look at the splitting field over some field which contains, so if our whatever the field we have of f contains a primitive ri root of unity, then it follows that if we add one such root, we have the splitting field and the Galois group is abelian. Okay? Then, so, and alpha I is the root. Then f of alpha I is the splitting field of this polynomial over f, and the Galois group of f of alpha I over f is abelian. And somehow this we would like to be kind of the abelian steps in the in this kind of chain of normal subgroups. So in order for this to possibly work, we need to have all the roots of unity that we need, so that this argument is true. So therefore we have to add all the r'th roots of unity for all I. And we can do this by just taking the following, so that m be the greatest common multiple of R2 to I. No, we have here, it starts with 2. Let zeta be primitive mth root of unity. So then, if I have take theta to the m divided by I, this will be a primitive ith root of unity. No? Because if I take it to the rth power, I get 1, because that's theta to the n. And if I take it to any smaller power, I don't get 1. So is a primitive rith root of unity. So thus, if we just add this one element to all our fields, we have all the fields, all the roots of unity that we might ever want to use. So
m is the smallest common multiple.
Yeah, the smallest, sorry. Yeah, I mean, I don't know what the greatest common multiple is. Obviously, you can take anything which is bigger. That would also be okay, but I mean, which contains this as a factor. Yeah. Okay, then I will soon stop. So thus we put F to be to be K, where we join this primitive mth root of unity. Then F contains primitive Ri roots of unity for all I. I think it was N. So now we can put now F0 equal to K, F1 equal to F, and then, so remember that we had Ki was equal to always Ki minus 1 of alpha I, no, in this chain before, and so we have Fi equal to Fi minus 1 of alpha. Okay, and so on until Fn equal to n minus 1 alpha. Okay, so we have just made all the fields bigger. So we had added this one step here before, and then all the other fields are just obtained by doing this. So thus we have this chain. F is contained in F0, Fn, such that the Galois group of Fi over, so that, so this is a chain of intermediate fields. The Galois group of Fi divided by Fi over Fi minus 1 is abelian for all I. No, because this is what the statement says, then the Galois group is abelian. When I add an element, once I have the roots of u. And so you can imagine that, so we will want to obtain, so this will give us, if we look at the corresponding Galois groups of these Fi's, so what we want to show, so we first want to show, maybe I will stop here, otherwise it takes too long. We want to show that so F so how do you want to say it? Well, maybe I will just want to show. We want to show that if we look at this statement, we can look at the chain. So this is the first step to show. If we look at this chain, the Galois group of Fn over K contains the Galois group of Fn over F0 contains the over F1 contains the Galois group of Fn over F2 and so on until the Galois group of Fn over Fn. So we want to show that this chain is such a chain of subgroups of the Galois group, such that each one is normal instead of inside the next, and the quotient is abelian. So we want to show that this chain shows that the Galois group of Fn over K is abelian, is solvable. So this chain of groups, we want to show this. And so this is the first one. And then we want to show that we have homomorphism from the Galois group of Fn over K to the Galois group of our original L over K, the surjective homomorphism. And so if this group is solvable, then this is solvable. Because okay. So that's how we want to proceed. But now it's I've tortured you long enough. So I will resume somewhere here next time. I should say that, well, maybe I can just switch off.